So this is topic 4. This is on non-uniform motion and acceleration. So what is acceleration? Acceleration is defined as any change in the velocity of an object during a time interval. This change could be increase or decrease in the magnitude of an object's velocity, or a change in the direction of the object. So you guys probably do know what acceleration is, like when you're speeding up in your car, and maybe that's a good word to use for that is speeding up. Oops. So that is basically what acceleration means when we think about it, but you could also be slowing down. So it can be in both directions. And when you speed up or you slow down, your velocity is changing, or the magnitude of your velocity is changing. You're not going at a constant. So that's what we would consider as acceleration and deceleration. So how do we calculate this? Well, this is our formula right here. It's acceleration, or average acceleration, is equal to our velocity divided by our time. And you notice there that there's some triangles, and they will tell us basically triangle, or that symbol means delta, and delta means change. So it's our change in our velocity over our change in time. And for some times you will only have one velocity one time, and other times you might have two velocities one time, two times one velocity. Whatever that may be, just know that you're going to take your final minus your initial, your final time minus your initial, and that will get you your answer to your problem. And one other thing to note here is that when we're dealing with acceleration, we are measuring this in meters per second squared. So in saying that, that is our new unit that we haven't used yet. Our velocity is still the same, it would be meters per second, and our time is in seconds. So how do we determine the deceleration the direction? The direction of acceleration is denoted by a positive or a negative, and it's the same as the direction of the change in velocity. So if the initial and final velocity are in the same direction, and the final velocity has a larger magnitude than the initial, then the acceleration was in the same direction. If the initial and final are the same direction, but the final has a smaller magnitude, then they're in opposite directions. And then the final one is if the initial and final velocity are opposite directions, then the object likely slowed down. Honestly, you don't really even need to understand any of that. You just need to be able to do the math. If you have your positives and negatives in the proper spot, then you will get the right answer to your problem. Okay, so let's try one of these, or maybe two. I'm going to Okay, I'm just going to read it through here, and then I'll go over to a note page so that we can do this out. So it says, a biologist observes a cheetah reach a speed of 19 meters per second. So 19 meters per second, that is a velocity. That meters per second is going to tell us. From a standing start. So what this is telling us is that when they started, they're standing. When you stand, you're not moving, right? You're staying in one spot. So this is also another velocity. All right, and that velocity is 0 because you're not moving. This velocity is where we're starting, so that's considered our V1, and this would be our V2, is 19 meters per second. Okay, and it says this all happened in a period of 4.3 seconds. That would be a time. And then it says, what is the cheetah's acceleration? I think I can do this right at the top here. I'm going to. So our formula is acceleration is equal to velocity divided by time. And for us, we've got acceleration we don't know. Our velocity is 19. And our time is 4.3 seconds, I believe. Yes. Okay, so I put my velocity as 19. If you want me to, I can put this as V2 and V1 is 0. because when we do this out, we are going to take v2 minus v1 divided by our time. So for us, our v2 is 19 meters per second, minus our velocity 1, which is 0 meters per second, all divided by our time, which we know is 4.3. Excuse me. So what we do here is we go 19, excuse me, geez. 19 minus 0, which will give us 19. So that's why I was saying we don't really need to write that, but I'm showing you how you might do it if you aren't standing or it's not a 0. 19 meters per second, and then that's divided by our 4.3. If we do that out on our calculator, we would go 19 meters per second divided by our 4.3 seconds, and that should give us 4.42 meters per second squared. Okay, so that's how you calculate that. That would be our acceleration. So hopefully I did that properly. So the next one, it says a car merges onto the highway traveling at a velocity of 14 meters per second. So this is our velocity. After 5.5 seconds, that's a time, the car reaches a velocity of another 28. All right. So you're traveling on the highway and you merge. You're originally merging at, You're originally merging at 14 meters per second, and then you finally reach 28. So that's our V1 versus our V2. You sort of like where you're starting is your V1, and your V2 is where you're ending. Then we want to find the average acceleration. So we're going to be using the exact same formula. Acceleration is equal to velocity divided by time. We've got two velocities here, so we need to do our V2 minus our V1. And it's divided by our time. Okay, our V2 in this case is 28. Minus our starting, or our V1, which is 14. And then that's divided by time. Our time is 5.5 seconds. So if we do that out on our calculator, I'm going to just do my 28 minus my 14, which you probably know is going to be 14. And then we need to divide that by 5.5 seconds. So if we take that and we divide it by 5.5, we will get an answer for our acceleration. So for this one, our acceleration is equal to 2.55, and that's in meters per second squared. Our last one here, it says objects near the Earth's surface fall with an acceleration of 9.81 meters per second squared. So this is actually gravity, and we'll be coming to that a little bit later, but that is our gravity and that is our acceleration. So if you drop anything on Earth, it's going to fall towards the Earth at 9.81 meters per second. All right, that's just how much pull the Earth has on masses, I guess you could say. So here we've got a couple things. We've got nothing. We've got an acceleration at least. I'm going to write that down as 9.8. If you dropped a rock from a cliff over a river, how fast would the rock be falling 4.1 seconds after you dropped it? So we've got a time as well. We've got 4.1 seconds. Okay, so as long as we have those two things, we can actually solve for our missing variable, which is our velocity. They're saying how fast. Our formula is A is equal to V over T. And we're going to need to rearrange that because we want our velocity to be by itself. To do that, we want to get rid of this divided by t on the right side. So we always, to get rid of it or to rearrange our equation, we do the opposite of what is there. And what is t doing? It's being divided by t. So we're going to multiply both sides by t. All right. So in doing that, we're going to go a times t is equal to v. All right. So that is all that we need to do. Then we just need to plug in our numbers. So, geez. Our acceleration here is 9.81 meters per second squared, multiplied by our time, which is 4.1 seconds. All right. So to do that, we go 9.81 multiplied by 4.1, and we get 40.221. All right. That's a velocity, so it's in meters per second. And that's basically it. All right. So that is our, I guess, practice problems using acceleration. And you'll have some of those in your assignment. How do we graph acceleration versus uniform motion, displacement, time graphs? Well, if we look at these, it says the graphs above demonstrate uniform motion. The slope of the graph is indicative of the magnitude of the object's velocity, while the direction of the slope is indicative of the direction of the object. So if we're looking at acceleration, if we look at this very first one, the object is at rest. There's no change in its position over time. So it hasn't moved, is what it's saying. So it's got no velocity on it. It hasn't moved. If we look at the next one is going up. Hopefully you know up is positive. It's moving at a constant speed, or constant in the direction from starting point. And in that, it's going to be a positive. So not moving it's constant in positive direction. And then our last one here, the object moves in a constant direction from starting point in a negative. So constant and negative. I don't know why my pen is being weird. All right. So how graphing accelerated versus uniform motion displacement time graphs. It says the graphs below represent non-uniform motion or accelerated motion. Because the slope changes depending on the points chosen, the object is not maintaining a constant velocity. So these ones above, that's literally constant velocity. There's no acceleration happening because everything's staying at the same speed. In this case, when you see a curved graph, you're going to notice that there's obviously an increase or decrease in speed. So this is known as an increase or an acceleration, and this one is known as a decrease in acceleration. Decrease. This graph represents uniform motion. The object maintains the same velocity over the 15-second time period. So if we look at this graph, we've got velocity on the left and time on the bottom x-axis. And by looking at that graph, I guess what they're saying here is that it maintained a constant speed because its velocity stayed the same. That's that line I just did. And basically it's showing us that if we, maybe that's going to say it on the next slide, but if we look at a graph like this, we can draw a line down and we could find the area of this. And in finding the area of that, that's going to give us an idea of what its acceleration is. So that's how we find acceleration on a velocity time graph. We just draw sort of a shape from the curve and then we're able to figure out the acceleration. These graphs represent non-uniform motion. In graph B, the object is speeding up. In graph C, the object is slowing down. The slope of the velocity time graph represents the object's acceleration. The area under the slope represents the object's displacement from its original position. So, being able to look at this, we can sort of see where it's going. You can see that on the very left graph, it's going up, which means it's a positive slope. And then we can figure out that acceleration. And then on the C graph, or the one on the right, it's a downward slope, and we would know that that acceleration is going to be in the negative direction. So it's decelerating. It says, example, this object traveling with uniform motion, is it speeding up or slowing down? So if we look at this, I hope you would know that it's not uniform, because there's each second, there's different space in between them. They've gone a different amount of distance between each second or time interval. And hopefully you notice that as we move on in time, there is more and more space in between. They've gone more of a distance, like from 4 seconds to 5 seconds than they did between 2 and 3, for instance. So by looking at that, you should hopefully know that they're speeding up. If we plot this data, these data points, we can see that the object is speeding up or accelerating, and the slope can be used to determine the rate of acceleration. All right, so if we were to plot this information, then we would be able to figure out that, yes, this is an acceleration. It's speeding up, and we could figure out the slope by finding this area under the curve. All right. So that's all you really need to know for your topic 4 assignment. Please let me know if you have any questions, and I'll be around to help you out.